All right, so this is one of our last videos. It might be actually the very last video because unless I make a question session for you guys, if you have any question session for that. And it's a very connected topic, and when I teach it, I usually teach it very connected as a whole thing. It basically covers all the things you need to know, but I may not do everything in the same exact order as your book does it. But I hope you guys have read this section and you guys are in the chapter and you guys are familiar with the words that I'm going to use, the terminology I'm going to use, and so forth. If not, at any point, feel free to either pause the recording or look back to the book if there is something that you're not quite sure what I'm referring to. Or you can also send me a message and mention the minutes where something is not clear what it's said. And then I can either as a comment on the video on YouTube, or you can just send me a message and I will be able to help you with that if some of you guys have that. So the idea is, I don't know if it's I would call it an application integration, but it sure is something that is very much something you will see probably more in your future classes as you go, especially if you're an engineer, you will see it a lot. And it has a lot to do with a real life, I would say, application of mathematics, and integrals play a big role in this concept. And the concept is what we call differential equations. So this is chapter 9, by the way. Now we do have a course at the end of most colleges that is called differential equation, and it's for us is math 2A. So after 1B, you take 1C, 1B, and then 2A is you can take 2A after 1B. And then, of course, after that, there are upper division courses for differential equation. Then we have partial differential equation, ordered differential equations. And it's basically the modeling feature of mathematics. It's done, usually, a lot of times it's done with the differential equations. And you probably have students refer to them either as DE or they're talked about as DPQ, depending again who your friend is and which teacher did they have, and then they refer to it as either of those. Differential equation is as simple as having a something like this. You have an equation, this is an example of it. You have an equation that involves a function, its derivatives, and maybe some function of the independent variable. So here y is a function of x. The solution to the differential equation is a function y. That's what we're trying to solve. So for example, say, let me just show you y double prime plus 5y prime plus 6y equal to, say, 0. Then y equal to c1 e to the negative 3x plus c2 e to the negative 2x is a solution to this differential equation. If you don't believe me, but let's calculate it. Y prime would be negative 3c1 e to the negative 3x minus 2c2 e to the negative 2x, and y double prime would be 9c1 e to the negative 3x plus 4c2 e to the negative 2x. Plug it in, you get 9c1 e to the negative 3x plus 4c2 e to the negative 2x for y double prime. For y prime, you get negative 3c1 e to the negative 3x minus 2c2 e to the negative 2x. And for y, you put in to check if it is a solution that would have to hold, the equality should hold. So I have negative 9c1, negative 15c1, and 6c1 e to the negative 3x. 4c2, 5 times negative 2 is negative 10c2, and 6 times c2 . And of course, this is equal to 0. it will be 0. So yes, it is a family of solution. Now these two, the C1 and C2 are called the parameters. So it's a two-parameter family of solutions. This differential equation is called homogeneous because it's 0 on the other side. There is no term that doesn't have y, y prime, y double prime, any of those in it. So it's called homogeneous. The solution is y equal to this, is a family of solutions. And so forth. As I said, the discussion of differential equation can be a very deep discussion. We spent a full course discussing the things I'm saying today in details with different examples. But what we're trying to do is just give you a quick guide, a quick reference to what differential equation and at the level that it will help you in your physics classes. So if you take like 4B next quarter, then you have the understanding of differential equation if your teacher uses that to solve some of the models there. Some classic models that can be we can use differential equations to set up and solve any kind of amount that changes constantly. So dy dt is a constant multiple of y. This will be your investment. This will be, and I will solve this for you guys. Actually, this will be your population growth. Now, if I change that, and of course here k is positive, if I change that to dy dt equal to negative ky, where k is negative, k is positive still, but with the negative, it's going to be negative multiplier there. Then this would be something like, the solution would be something that could be used for, say, radioactive decay, which leads to like carbon dating and so forth. We'll talk about both, and I'll show you guys how to solve them. The population growth one, this one can actually be better modified to match the logistic factors. This is called the logistic model, in fact. And so on and so forth. Other examples of differential equations, the models are springs. A damped spring model would look like something like this. Where m refers to mass hanging from the spring, beta refers to the damping factor, and k is a spring constant. Probably have seen that model before. And actually, the solution to this model would be a sinusoidal graph. So that's why the springs go up and down, up and down, up and down. Now, it may be damped. So the solution would be sinusoidal, of course, if it's not critically over damped. If it's under damped, then we have a damped harmonic motion. If there was no damping, then it would actually be actual sine wave. Again, the details are not very important right now. We don't solve anything like this in this class. In 2A, you will solve this. It's part of the very first second order differential equations. I mentioned second order differential equation because it's a second order. The highest order derivative is 2. So it's a second order differential equation. Once again, this is homogeneous, right? Okay. So this is the basics of differential equation. If you read 9.1, more or less all it does is Stuart is trying to give you guys motivation on why you need to study differential equation and what are the applications of it. So he talks about the population growth, he talks about the logistic model, talks about strings, and literally he just talks about it. He doesn't do much with it. And that's enough. That's enough. Like 9.1 is not a very fancy section. It's just like basically saying there is this thing called differential equations. These are the places you can see them or use them. And just stay focused on this because you're going to see more of this in the future. So that's the purpose of that section. A good read for sure, but don't think too much about it. The next thing about differential equation is now that we know differential equations, what they are, and we know what is meant to solve a differential equation, the solution is the y. We discussed it just a few minutes ago. That's the solution is the y that solves that. We in fact need to talk about now a particular type of differential equation that we have a nice method of solving. And that's basically the only method we introduce in this class in solving it. There is a lot, there are different methods. In fact, your 2A is called, it's a first course in differential equation, which is a real techniques class, how to solve different types of differential equations, a little modeling as well. But the type of the differential equation that we're going to solve in this class are what we refer to as separable. So this is the topic in 9.3. A separable differential equation is one that looks like this. You have dy dt is equal to some f of xy. Now, what makes it separable is if that f of xy can be written as g of x times h of y, purely a function of x times purely a function of y. If we can split a function into product of two functions, one purely in terms of x and one purely in terms of y, then that function is called separable, and the differential equation is called a separable differential equation. So some examples of separable functions would be, say, x squared y cubed, where here your g of x is x squared, your h of y is y cubed. So this is separable. X squared plus y cubed is not separable. You cannot write it as product of something of x only and something of y only. X squared over y cubed is separable because you can write it as g of x is x squared, h of y, and I'm sorry, I'm using the same powers, but it's because it's irrelevant as long as you have that one. This is separable. E to the x squared plus y is separable because you can write that as e to the x squared times e to the y. So g of x is e to the x squared and h of y is e to the y. 1 over x is separable because your g of x is 1 over x, h of y is 1. Sine of x plus y, a lot of students think this will be separable because they remember the trig identity, sine x cosine y cosine x sine y. But even with that identity, this will not be separable. So these are some examples of separable and non-separable differential equations, functions that can be used in differential equations. Now again, we're not going to deal with cases when it's not separable. That's not our focus right now because we don't have tools. We don't have, and we won't have tools to solve this. But we want to focus on the cases where they are separable. So I'm going to show you guys with an example how to solve a separable differential equation. And I think that will kind of like show you what the approach is. So suppose dy dx is equal to, oh, I put dy dt, my apologies here guys. I put dy dt, suppose with dy dx. Yeah. Yeah. So suppose dy dx is equal to, let's make our life a little bit easier. Let's just say x over y. Okay. Now, what you could do here is you can separate them as y dy dx is equal to x. Just bring the y up. Then integrate both sides with respect to x. Then by chain rule, the dx's cancel out. And to the y dy is 1/2 y squared plus c1. And the derivative of x dx is 1/2 x squared plus some c2. Of course, I can put the c1 and c2 together. Let's call that a new c. And let's multiply and call that even newer c. So that will be the implicit form of the solution to this differential equation. Not too bad, right? The challenge is really the integration part. And that's why it's in this chapter, it's in this class, because we need to integrate. That's the biggest challenge. Some of the integrals are going to be very straightforward and simple. Some will be a little bit more involved. Regardless, it's not something that you cannot do. Let's look at the problem together. Now, before I move on, a lot of times you will notice that a lot of people don't write this step. So what they do is they're like, okay, I take y to that side, I take ds to that side, I get y dy is equal to x dx. And then I integrate it. So they go directly to that step. Nothing wrong with it because the supporting step is this. The reason you can do it is because of this. But it's just every time you can write this and then this. So there's no need for it. So if you see like people going directly to this, it's just fine. Oh, so let's do an example. Yeah, there are a lot of very good ones here. I'm trying to find some that you guys would enjoy. Yeah, let's do number 6. Let's do number 6. And I want to talk a little bit about IDP. So let's do number 6. This is a 9.3, number 6. It sounds exciting. du dt. One thing that you have to be careful here is you will see a lot of different variables used, different variables used. That's Stewart's way of telling you, well, when you start modeling, don't expect every variable to be your classic x and y. You can have u, you can have t. T still is faithful to time. So usually when you say t, your parameter is time. But you could have different variables. So don't get too attached to using x and y for everything you do. Okay. So first things first, I need to see if it's separable or not. So I'm going to rewrite it as 1 plus t to the 4 over t squared u plus u cubed, u to the 4, sorry. And which is 1 plus t to the 4 over t squared times 1 over u plus u to the 4. So it is in fact separable. So let me write it clean here. du dt is equal to 1 plus t to the 4 over t squared times 1 over u plus u to the 4. I multiply both sides by this and dt. So I get u plus u to the 4 du is equal to 1 plus t to the 4 over t squared dt. Then we integrate it with the corresponding variables. I 1/2 u squared plus 1/5 u to the 5th. There is a c here, but I'm just going to have a c at the end there. This integral is actually integral of 1 over t squared plus t4 over t squared. So integral 1 over t squared, actually, let me write it out. So I'll call this C1. Let me write this out. 1 over t squared dt plus t squared dt plus that. So that C1 is from this integral. Okay. So 1/2 u squared plus 1/5 u to the 5th equals to -1 over t, some c there as well, plus 1/3 u t cubed plus, I'm just going to call it a c that includes all of this. So this is I know your independent variable is u, your dependent variable is t. So, but this is an implicit solution to this differential equation. And you can just leave it like that. On the test or anywhere else, just leave it like that. Okay. Basically, all of these problems, the trick is to integrate it. Once you separate it, then you need to integrate. Let's do number 13. Let's do number 13 together. Okay. Yeah, it's a fun. So I don't know. Again, I don't know what flavor of mathematics you like, but if you like this and you're thinking of majoring in mathematics, and again, just throwing it out there, I would say that you like applied mathematics side. So if you're looking at school and that's what you're trying, because if you like differential equation, that's basically the kind of things you like. Yeah. Okay. Now, what is this? This is what we refer to as an initial condition. With the initial condition, your differential equation becomes an initial value problem. It's referred to as IVP. So you hear IVP a lot when you learn differential equation. And that means you have a differential equation. In addition, you have in some condition. Remember when we solve and when we integrate, it was the same thing, right? When you usually solve, you get a constant that creates a family, right? Creates a family solution. I don't know if you guys remember when you were integrating, your antiderivative is a family of solutions, not a fixed solution. Now, if somebody tells me a particular point on my family of solution, then I am fixing that point, which means my solution is this curve and no other curve, because that's the only curve that meets this condition. So IVPs, and there's an existence uniqueness theorem in differential equation that you guys will learn. And what it says is basically that IVPs under certain conditions will always have a unique solution. So that unique solution is really that function that you get fixed based on your initial conditions. So that's what IVPs are. Now, there is also something called boundary value problems. These are initial value problems, and there are boundary value problems. The boundary value problems, which you don't do much of it in this section, in this book, would not have a unique solution necessarily. So this is a distinction between. And they give you boundary values rather than initial conditions. Let's not get stuck on that too much. It's not a big focus of what we do in this class. Anyways, so after I solve this, I need to make sure I don't have a constant because I will plug in my initial conditions to solve for that constant. So 2u du is equal to 2t plus secant squared t dt. So a lot of things look familiar, right? 2u is u squared and 2t is t squared, and antiderivative secant squared is tangent. And you have a c. And this is what I was talking about. You are going to have a constant that you have to solve for based on your initial condition. U of 0 is -5. So 25 is equal to, if I plug in -5 for u, I get 25 is equal to 0 plus tan of 0, 0 plus c, which means c is equal to 25. So I have u squared is equal to t squared plus tan t plus 25. But here's the thing. That is not an explicit solution for u because this u squared is equal to this. So technically, u would be plus or minus square root of t squared plus tan t plus 25, right? It could be either plus or minus. Because they say u of 0 is -5, then you won't add 0 to get a -5. So if I put 0, 0, 25, square root of 25 is 5. And since I want to get a -5, then I don't have a plus or minus. I only have the minus version of that. And that's the explicit solution for your differential equation. It's a little technicality there, but yeah, you need to worry about those things. what your initial condition is, what does it lead to the constant to be, and how to express the function explicitly. As you do the homework, you play with more of these. But I promise you, it's not going to be anything. I would say this one is probably in a medium to higher level of difficulty for this section, just because of the technicality with the negative and the secant, maybe it's not friendly for you to integrate. But everything you'll have here will be separable. You know no other way of doing it, so everything should be separable for you to solve it. In 9.1, there's some problems that you actually have to verify something is a solution. Here you're solving. And if you really have the time and interest, plug in your solution in the initial differential equation, see if it satisfies. It's not necessary. If I'm doing a test and I have like an hour to do the test and there's about 10 questions, then I probably am not going to put too much focus on checking these things because it's going to eat up my time unless I have done everything and I just need to check my work to make sure that I know it's correct. But as I said, don't do that unless you have extra time. With understanding of separable differential equation, I can actually go back to some of the models I introduced you guys earlier, and I could try to solve these with this because all of the models I put up here for you guys are what we call separable, right? So they're all separable. This is ky separable, negative ky separable, and even this is separable, right? Remember, m and k here are constants. I have a name for m. I'll let you guys know in a second. Let's start with the one dy dt equal to ky. So right. So the one is dy dt is equal to ky, which means 1 over y dy is equal to k dt. Integrate both sides, you get natural log of y is equal to kt plus c. Y is equal to e to the kt plus c, or e to the kt times e to the c. That's a constant. E to the c here is always greater than or equal to 0. In fact, positive, not even equal to 0, because then it would collapse. But since I have absolute value, I can remove the absolute value and I replace the e to the c with just a constant a. And now that a is not necessary, it could be positive, it could be negative, or it could be 0. Again, 0 would not be a good option because then the whole population would be 0, or the amount would be 0, whatever the amount represents. You have seen this. I'm confident you have. If you've taken pre-calculus or any algebra class, you have seen this model. It's called the exponential growth model. I'm pretty confident you have seen this. You probably have seen it for investments. The investment, the compound continuously, was your final amount was initial amount e to the kt, but we you wrote it as a equal to PERT, where P is the principal, R is the rate, T is time, and A is the final amount. So that was, again, if you took a pre-calculus course or if you took a algebra course here, we cover this model, not the differential equation model that leads to this solution, but just this as your exponential growth model. Population grows like this. But again, as I said, we have an adjustment to it to make it more realistic. Exponential growth model has a feature called the doubling time. The time it will take for an initial amount to double. So I want my amount to be twice of what I start with. Is it clear why we call A the initial amount? Because that's an amount when t is equal to 0. And if t is equal to 0, e to the k 0 is e to the 0, which is 1. So A would be the initial amount that you will have. So A is canceled out from both sides. 2 is equal to e to the kt. Natural log of 2 is equal to kt, or t, the doubling time, is natural log of 2 divided by k. Okay. So that's something about exponential growth to know. The flip of that, literally flip of it with respect to the y-axis. So the flip of that is the model where we have dy dt is negative ky. Again, we're assuming that k is a positive constant in both cases. So the negative carries the negativity for this. So once again, 1 over y dy. I usually don't take the negative with me. I leave it up there. Once again, natural log of y by integration is negative kt plus c. Y is equal to e to the negative kt times e to the c. And y is equal to a e to the negative kt. This is called exponential decay model. The things that decay exponentially are carbon are radioactive decay. Drug in bloodstream decays exponentially. We have Newton's law of cooling, which the drop is exponential. So those are examples of it. Now, exponential decay has a feature called half-life. Half-life is the amount of time it would take for some amount to be down to half of it. So we can use the initial amount A as our amount that we consider. So I get 1/2 A is equal to A e to the kt, negative kt. So notice I just replace y with 1/2 A. I want to know how much time it will take for it to be half of what it starts with. A's cancel out again, so the initial condition makes no difference. Then natural log of 1/2 is equal to natural log of e to the negative kt, or just negative kt. Or t will be natural log of 1/2 over negative k. But notice 1/2 is 2 to the negative 1, and the negative 1 can come up front by log properties. And the negatives cancel out, you get the same. So half-life is natural log of 2 divided by k. Same exact formula as doubling time. And that's because of symmetry, right? If you think about an exponential growth model, looks something like this. Exponential decay model looks something like this. So the amount it would take for exponential growth to double is the same thing that it would take for exponential decay to half. So this is t doubling or t half, depending on whether you use decay or growth. It's just a symmetry of the graph. So one of the things about population growth, the model that I told you guys where it is dy dt is equal to ky. The problem with that is its result is an exponential growth model, which grows without bound. You just saw that the answer would have been like y equal to e to the kt, a equal to the kt. And that's obviously is not a reasonable model for long term. There's no way population will grow without bound in that location because of all the logistic issues. A population cannot grow without, because people require the resources, right? The food, the land that you have to grow on. So, I mean, even if you ignore everything else, at some point, there's going to be more people than the land can hold. It's just unrealistic, right? Exponential growth is not a realistic model for population long term. You could use it short term, but not long term. It just happens that if you have more population, actually the growth should slow down because they're fighting for resources, right? That's the logical way of thinking about it. Like you cannot just have grow without bound. So at some point, you should say, well, okay, it's getting too much, so it's going to slow down in growth. And that's the feel of the logistic model. We tame this model by introducing a factor m minus y, where here m is what we call carrying capacity. In simple words, it's the maximum amount you can have for that population. So the land can only hold 1 million people, then m would be 1 million. that kind of thing. Now, this model is more realistic because here's what happens. You would expect if y is small, even though if y was small in the normal traditional exponential model, it will be the only factor that affects the growth. And if y is small, you would expect a slower growth. But in reality, if y is small, that means there's a lot of resources for people to use, which means actually the growth should not be tempered too much because it should not be just the y part, right? There should be something else that helps the growth, in fact. And then m minus y is supposed to be the balancing act here. Because if y is small, m minus y would be big. So the two will balance each other out. In the other side, if y is too big, even though it will contribute a big part to this factor, it still should not be the only deterministic factor because bigger y means there is more fighting for the competition for the resources, right? And m minus y would balance that out because m minus 1 y would be small. So say if m is 100, if y is 1, m minus y would be 99. So balance out. If y is 99, m minus y would be 1. They balance out. So it's kind of like a balancing act there. There are other forms and versions of this model, but this is the one that I feel makes more sense to students, and students can relate to this. Once again, this is a separable model. So 1 over y n minus y dy is equal to k dt. And I can integrate them corresponding variables. Now, if you remember from section 7.4 of your book, the left-hand side is actually what we call a partial, requires what we call a partial fraction decomposition. So I need to do a partial fraction decomposition on 1 over y n minus y. So I'm going to say that's a over y plus b over m minus y, which means 1 is equal to a m minus y. Again, remember you treat m as a constant, plus by, which means 1 is equal to am minus ay plus by. 1 is equal to am minus a minus by. So am would have to be 1 and a minus b would have to be 0. So a is equal to 1 over m because am has to be 1, and a minus b has to be 0, which means b is equal to a is equal to 1 over m. So the left-hand side becomes 1 over m y plus 1 over m minus y. dy is equal to kt plus c. Now this one is easy to integrate. That's 1 over m natural log of y. For this one, I'm going to do a u sub. I let u be m minus y. The u is negative dy. So it's integral of 1 over m u with a negative front. So 1 over m natural log of y minus 1 over m natural log of u. Now u is m minus y, so m minus y, with kt plus c. Let's multiply everything by an m and make it a little bit easier for ourselves. Natural log of y minus natural log of m minus y is mkt. And I'm going to introduce a new c, which is the previous c times m. You can do that, but do it with, make sure you're comfortable why you're doing it. Introducing a new c. Then log properties tells me I can rewrite this as log of y over m minus y in absolute value, mkt. Take both e to both sides power. Introduce an a. To get rid of the absolute value. Now I can have fun with the algebra of it. And then y is equal to am e to the mkt minus ay e to the mk. I'm just really having fun with algebra right now. This is take this to the other side. Y plus ay e to the mkt is am e to the mkt. Again, remember, just a reminder, m is the carrying capacity, k is the rate, corresponds to the rate. Not quite the rate, but corresponds to the rate. T is the time variable, so T is a variable, and also is Y. Y is a variable as well. But everything else, A, M, and K are constants. Divide by that. Now, what I'm going to do is I'm going to do something fancy. I'm going to multiply top and bottom by e to the negative mkt. And if somebody says, what is the limit as t goes to infinity of y? As t goes to infinity, this part goes to 0, I get am over m, which is m. That's what you would expect. You would expect that eventually the population would hit the maximum carrying capacity. Now, on the test or final, what I would do is well, actually, this is not going to show on the test today. This will only be on the final. What I would do is probably I will give you the value for k, and I will give you the value for m. So from the beginning, the model you will have, you will be given m and you'll be given k. So you start with numbers. And I'll probably give you some initial condition for the population as well. So you can solve at the end for that A. So if they give you some initial condition, you can plug in for Y, and you already know M and K. So you plug in for Y and T, then you can solve for A. So that you may be given a question like that. But if I give you that, I will give you solid numbers for K and M. And you have to just start from here with those numbers and then go through the whole process of differential equation solving that I introduced in this section. This is a logistic model. You probably have seen the graph of it. It looks something like this, where M is your carrying capacity. Somewhere in between, like halfway, it changes the concavity. It's inflection point. It doesn't have to be on the x-axis, but my drawing seems to place it there. But somewhere halfway, it changes the concavity. So that's what we call the inflection point. And it's right at level of m over 2. Okay. I hope this is helpful for you. I hope it helps you to do the problems. This is the last discussion for this class. I may make another video to just fill in the holes and the blank, whatever I didn't cover, or the question based on the questions I get. As I said, the homework for this is not going to be due until next week anyway, so you have plenty of time to do this and do the reading assignments and so forth. But feel free to ask me questions, and I'm also willing to make a homework video for any problems related to the final, anything from beginning of the class to this point. So feel free to ask me any of those questions as well. Other than that, I hope this is helpful, and let me know if there's any part of this that you have questions about, or you want me to clarify for you guys, either through office hours or post the comments on either YouTube or my through Canvas, and I will be able to help you through either making another video or just explaining to you your answer to your question. All right, thank you so much, and I'll see you guys for test 3 and for final.